So in the past video, we have discussed how to compute for Anova in a manual way. And right now, we will be tackling how to compute Anova using Microsoft Excel. So without further ado, let us jump into our discussion. I will just share my screen. Yeah, so before this video, I have a couple of videos tackling the terms that you need to know before performing Anova and what are those, how to compute those in the manual computation video. So for this video, I will be using Excel and I will demonstrate how I use Excel in computing for Anova. But a video after this, I will post the easiest way on how we can evaluate or statistically treat our data. Yeah. So for the information of others, I am speaking in English because there are some viewers of this channel who are from other countries, and I am receiving comments that I need to speak in one language, and I think that if I will be speaking in English, everyone can benefit and everyone can, understand our whole conversation. So let us do this. Okay, so we will be using my example from the past videos, and it is this one. An experiment wants to determine the yields of 5 newly introduced varieties of corn using completely randomized design. Each type of corn is planted to 4 plots of land with equal fertility and grown under uniform cultural management practices, and the yields in units of 100 bushels are shown. Can we conclude that the mean yields of the 5 varieties of corn are the same using 5% level of significance? So first thing that you need to do is to get your results. So this table right here, the table showing the varieties and plots, these are your results. 9 100 bushels, 8 100 bushels. That is these values. Yeah, so what we first need to do is to arrange our data. So how will we arrange our data? This is how I do it. For variety, I will place, we have 5 different varieties, right? So I will place here A, and since we have 4 replications, 4 plots, 1, 2, 3, 4, I will place A in 4 times. Same through with B, I will also place it 4 times. C, 4 times, 4 times, D, and lastly, E. Yeah, so that's it. So the plots, for me to actually know the labels of each plot, I will place 1, 2, 3, 4 here. 1, that means plot 1, plot 2, plot 3, and plot 4. So I will just copy paste all of this. Yeah. So after that, I will input the result, which is indicated here in our table. So it is 9, 8, 9, 10, 15, 13, 16, 14, 5, 4, 4, 9, 11, 10, 9, 9, 14, 4, 7, 6, 7. So make sure that your input here is the same as your obtained results. So you need to double check it if it's 9, 8, 9, 10, right? 9, 8, 9, 10, 15, 13, 16, 14, 5, 4, 4, 9, 10, and 11, 10, 9, 14, and lastly 4, 4767. Okay, so that's it. You have already arranged your data. Now what you need to do is to complete your ANOVA table. Before that, let us first identify our N and our T. So N is the total number of experimental units. And in our case, it will be 20. Why 20? Because we have here, actually the formula for N is T times R. T times R. T is your treatment, which is we have 5 treatments. So 5 treatments, and our R is our replication, and we have 4 replications for this case. Thus, our N is 20. Our T is 5. And so that's it. So the next thing that you need to do is to compute for the treatment totals. When we say treatment totals, those are the sum of every yield per treatment, or every whatever variable you are looking for. For example, if you're looking for the height of a certain plant, the centimeters of your plants will be also total. So that will be your treatment totals. So in using Excel, luckily we have different formulas here. So we will make use of this formula. So let's go for sum, and then we will highlight. What happened? Wait. Okay. So this would be equals sum. Then you're gonna highlight this 4. So that will be it. Next. Next one is this one. Do the same. Sum 1. So include here sum 1. So we already have our treatment totals: 36, 58, 22, 44, and 24. So those are our treatment totals. So what we need to do next is to calculate the grand total. So for the grand total, we will still do the same sum, and we can highlight these 5 and 2. We will arrive with 184, which is also the same when we computed it manually. It is also 184. Okay, so for this, the next thing we need to do is to calculate this thing. So first we have DF for the treatment. So this is in this part of your ANOVA table, if you can remember from our past discussions. This is your ANOVA table, right? So for DF, TR, it is T minus 1. And I will just zoom out. T minus 1. So here we have established that our T is 5. We have 5 treatments, variety A, B, C, D, and E. So what you need to do is 5 minus 1, that would be 4. So for DF of error DF, we have our N, which is 20, minus our treatment, which is 5, and minus T, that will lead us to 15. And for our total DF, it is N minus 1, which is 20 minus 1. Thus, we will arrive with 19. So if you will compare it here with our final ANOVA table, our answers for when we computed it manually, they are the same. 4, 15, and 19. Okay, so next, let us have these. First is our correction factor. So the formula for correction factor is G total, which is our grand total, squared, then over our n. So to do that, here in Excel, we do not have like the what it is like in using a scientific calculator, because in our scientific calculator we can just place fractions like this. Yeah, so it is easier somehow to use this for formula with with division. So what we need to do here is to take it piece by piece. So first, let us have grand total squared. So we can do it by multiplying this. So our grand total is 184, right? So in order for us to get the squared value, we can have 184. When you are using Excel to compute, you always need to have an equal sign before your formula. Then 184 times 184, that is also equivalent to 184 squared. So we have this one. Then what you need to do is to divide it with n. So equal, then you can just highlight it, divided by what is our n value, n equals 20. So we will arrive in 1692.8. So this is already our correction factor. As easy as that. Next is the total sum of squares. Okay, so here what we need to do is to sum the squares of all the yields of all your results. So for this case, we have all of this. We need to sum all of this. So in our past video, when we computed it manually, we used calculator and we need to input one by one. But in Excel, all you have to do is to have an equal sign, input sum SQ, then have an open parenthesis and highlight all of these values and just press enter. Then you will have your sum of square of yields. But the formula doesn't end there. So in order for us to compute for the total sum of squares, we need to subtract the correction factor, which is 1692.8. So here we have 1958 minus this value. So we will arrive with 265.2. So this is already our total sum of squares. And if we will look back here in our answers for the manual computation, it is the same, 265.2. So the next one is to compute for the treatment SS. So for the treatment SS, we need to square. We need to square all of the sum of this one. So we need to do like, let us sum SQ. Then just highlight these 5 values. So these are the treatment totals as we have computed a while back, right? If you can still recall. So that's it. So that is the sum of square of treatment totals. But again, the formula does not end there. We still have this value to be divided by t minus 1. So t minus 1 is this one, our DF for the treatments, which is 4. So what we need to do is to have this one subtracted by our t minus 1, which is 4, which will it is not subtracted. Okay, that's wrong. Wait, this value divided by, I should say, divided by 4. So we will arrive with 1914, and once again we need to subtract the correction factor. So from this value, we will subtract the correction factor, which will give us 221.2, which is also similar to what we've computed manually. Okay, so the next steps are pretty much easier than these 3 factors. So we have MSTR. MSTR is just TRSS divided by t minus 1. So since we have already computed for TRSS, it will be easier. So we have 221.2, and we will divide it by T minus 1, which is also this one, 4. So that is 55.3, similar to our answer for our manual computation here. Next, we have ESS or error SS. What we need to do is to just subtract our TSS, and our TRSS. So we will arrive with 44, which is also similar here in this table. And lastly, MSE, which is ESS, which is this 44, divided by N minus T, which is our error DF, which is 15. So we have 2.93, similar again to what we have here in our answers. Now, for us to compute our F value, we need to just divide our MSTR over MSE. So to do that, you can just place an equal sign, then go with press that one, highlight that one, and slash sign, then our MSE, which is 2.93. So we have 18.8523. So this is our F computed value, which is also similar to what we have obtained here. Perhaps the reason why this is 18.87 is because it was computed manually. Because when we are computing manually, sometimes we round up, right? We round up or we round down. So perhaps we can try here 2.93. If it will be the same. 5.3 divided by 2.93. Yeah. It will be, that's the reason why it is 18.87. But this one kasi, it has a lot of decimal places, but thus this is more concise. This is more, what do you call that? Accurate. But it depends on your professor. You can ask them if they want you to round up or not, something like that. Okay, so well, this is our FC value. It is still somehow close to each other, and the way we can evaluate this is by comparing it with our F tabulated value. So where can we find our F tabulated value? So we can find it in our F table. Again, if we will look back in our problem, it stated using the 5% level of significance. Actually, the F tables can be browsed in Google. You can just search F table 0.05, then a lot of tables will just appear. Just look for reliable ones. So here we have so F tab, and our DF must be identified. So here, if we will look back at our Anova table, we have DF4 and DF15. So these are DF1 and DF2. So let's go with find the value that will cross in these two values. So for DF1, we have 4. I do not know if you can see my cursor, but I hope you will. DF1, we have 4. And DF2, we have 15. So if you will trace their common point, it would be 3.0556, this one. Here at the bottom part. So it's 3.0556. Now, what is our decision rule? The decision rule, as we've discussed on our past videos, is that reject null hypothesis if FC is greater than F tab. Decision rule F tab. So when we say reject HO, the null hypothesis states that all of these varieties of corn, all of your treatments are equal, are the same. That is our null hypothesis. Like for example, variety A is not different from variety B, and it is not different from variety C, it is not different from variety D, or it is not different from variety E. When it comes to the yield, that is the claim of your null hypothesis. Thus, we need to have this decision rule in order for us to see if there is a significant difference, if they are the same or if they are not the same. So here, we can clearly see that our FC, which is, let's say this value, 18.85, is so much greater than our F tabulated, which is 3.0556. Thus, because this value is greater than this, we can reject this hypothesis. We can reject this hypothesis. Thus, our conclusion is that at least one variety gives a different mean yield. At least one variety gives a different mean yield, which means variety A might not be different from variety B. Variety B, the yield of variety A, B, C, D, and E are different significantly from each other at 0.05. So a very good thing to add here is at 5% level of significance. Yeah, we can add that. Yes. Yeah, so this is it. This is our conclusion. So I hope this video helped you in order to compute your analysis of variance and interpret your result. This part is actually the interpretation of your results. So perhaps the question that you are asking right now is, which of the following treatments are different from each other? Because we have just concluded that at least one variety gives a different mean yield, but we are not yet specific to which of those varieties are really different from each other. Thus, we can do that by conducting our post hoc test, which is the multiple comparisons, and that can be another thing that we can discuss here on my YouTube channel. So I hope this helps. Again, thank you very much. Again, I am Arvin Joshua P. Berlongo for Sprout Up I6111 para sa Bayan, Agham at Agrikultura.